Hi, BC students. This is a correction video for the free response on the test. Maybe it'll get you a last minute idea before the AP exam, or maybe you'll just learn from a mistake, and that's cool with me too. All right, so in the first one, you're trying to make the series for F, which is this, based on the fact that they gave you inverse tangent. Some of you then didn't see the prime or didn't address the prime. So first thing, read the question really carefully. We're going to build f of x series, and then we're going to do f prime based on taking the derivatives of the terms. All right, so f of x then, which is equivalent to, or is the function inverse tangent over x, could be modeled by, now let's take this series and divide out an x. So we'd get 1 minus x squared over 3 plus x to the 4th over 5 minus x to the 6th over 7, and negative 1 to the n, x to the 2n plus 1 over 2n plus 1. And it keeps going after that. All right. Now we're going to take the derivative of each term. Derivative of 1 is 0. Derivative of negative x squared over 3 is negative 2, x to the 1st over 3, plus 4x cubed over 5 minus 6x to the 5th over 7. That's 3 non-zero terms, so I've satisfied that part. Now for the general term, remind you, you can always do the general term by either looking at the pattern in what you've already done or just doing the derivative of the previous general term. And so that's, in this case, that's what I'm going to do. So if I take the derivative on that, negative 1 to the n stays, over 2n plus 1 stays. And what happens when you take the derivative on that? Well, 2n plus 1, you bring down the power, 2n plus 1, and reduce it by 1. And that is not looking correct. Oops, I didn't. I'm dumb. Sorry. I make it sound so easy and then I can't do it myself. All right. The general term derivative this, when I divided out an x, negative 1 to the n stayed, and I reduced this by 1, so it became x to the 2n plus 1 reduced by 1, so x to the 2n over 2n plus 1. So when I take the derivative on that, it's negative 1 to the n, and 2n comes down, reduce it by 1, and the denominator is still there, all right? So that's what it should have looked like. That should have been a pretty soft 3 points, although I screwed it up. But I checked my work and caught my mistake. So you should never really be off on this, because you can say, does this work? Does this make this term here? For example, what does this mean? I'm starting with, if n starts at 0, it must be starting at 0 or 1, and then does that make the term? So you have a way to check your answer. Does it make these? Otherwise, the general term is wrong. So check your answer. All right, so looking at B, this I knew was going to be tough. This is one of the harder ones. It says, use the results from part A to find the sum of the infinite series. Now, if you're thinking it, if you thought this way, sum of the infinite series, that means I need to know a formula, geometric or telescoping. And so if you thought that way, I totally understand. But this series is definitely not geometric or telescoping. What you should instead is say, look, this is supposed to be the series for, look right there, f prime, with what value? So this seems to represent negative 2/3 is here, And it must be the case that they're finding f prime at 1 over root 3. Now you find the sum of the series then not by using the series, but by using the derivative of inverse tangent over x at 1 over root 3. And so by quotient rule on that series, you're going to say low d high minus high minus, some people put plus there, d low over the square of what's below at 1 over root 3. And then you plug in 1 over root 3 and evaluate. And while you don't have to simplify the algebraic terms, for example, you can leave 1 over root 3 and 1 plus 1 third, you do have to simplify the trig expressions. Inverse tangent of 1 over root 3, for example, is pi over 6 over 1 over root 3. So if you left it like that, you would get full credit. All right, let's go to C. Integrating is also a huge skill of series, all right? So if I integrate f, then g is plug in the series. Now, I didn't take off for this, and AP wouldn't, but when it's in the integral, you should be using t for the integral. So if I put in the series for f, not f prime, then that's here. So I need to say something like integrating 1 minus x squared over 3. So I'm integrating 1 minus t squared over 3 plus t to the, what is it, fourth over, minus, or plus t to the fourth over 5 minus t to the sixth over 7, okay. So the power on the top is even over 5. It's alternating 6 over 7. Oops. And so on. And they do want the general term. So it was something like negative 1 to the n, x to the 2n over 2n plus 1, t, dummy t, dt. Yeah? So here we go integrating again, just term by term. Integration of 1 is t minus integrating t squared is t cubed over 3 times the 3 plus integrating t to the fourth is t to the fifth over 5 times the 5 that was already there minus t to the seventh over 7 times the 7 that was already there. Negative 1 to the n, t to the 2n plus 1 over 2n plus 1 squared from 0 to x. Plug in an x doesn't do anything but change all the variables to x, and so x minus x squared over 9 plus x squared over 25 plus x or minus x squared over 49. And then you can see the last one. All right. Now, that said then, the last problem will make a heck of a lot more sense. G at 1 then would be approximately equal to the series that they're talking about, 1 minus 1 over 3 squared plus 1 over 5 squared. This is an alternating series. The terms go to 0, and they're decreasing. So it must be the case that the true G of 1 and that estimate is the same as the true infinite sum and a 3-term estimate, which is less than or equal to A4. A4 is the next term, which is 1/49th. If the error is definitely less than 1/49th, then it's also definitely less than 1/40th. And that's how it goes. Now, I chose this one because it was a good representative and didn't have interval of convergence like the AP test will have. But you need to be able to make a series like we did in Part A. You need to be able to take derivatives of series like we did in Part A. Part B was hard. That was meant to assess, the best from the good. There are several ways to get an actual sum. One is geometric sum formula, one is telescoping, another is if you know the series is equivalent to a function, then you can evaluate the function at that value. C is integrating series, which you need to be able to do, and D is alternating series error bound. So again, I felt like this was representative of big ideas of calculus. That's why I put it on the final. So I hope you learned from it, and I hope you have a great day. This might be the last video I make for y'all this year. And I don't even know if anybody will watch it, but I really wish you the very best. You've learned a lot of calculus, and I just hope you really show me what you know and show them what you know in the AP test. Goodbye and good luck.